Alright, hopefully you guys can hear me. I'm going to start going through the exam. These questions might not be in the same order as you, so if you don't see any of the ones that you're confused on, I'll be uploading them tomorrow. So the first one that I have on my exam is the question asking about an elastic or inelastic problem, or collision. Basically, an elastic collision means that the momentum before and after the collision is the same. So when you calculate your momentums for this problem, if they're equal, then the collision is elastic. However, if your momentum before and after the collision is different, then it's an inelastic problem. So, for example, in this problem, we have a 4 kilogram weight and a 6 kilogram weight. Before the collision, one of them is traveling at 1.8 meters a second, another is traveling at 0.2 meters a second. So if we want to calculate the momentum in total before the collision, it's pretty simple. Momentum is basically going to be 1/2 your mass times your velocity squared. So if you do that for both of the weights and combine them together, what you're going to get for the momentum before the collision is going to be 6.6. If you do the same thing for after the collision, you then have the same thing, 1/2 mass times velocity squared, you're going to get 6.6 again. Since these two numbers are equal, your collision is elastic. And that's the answer for this problem. They're perfectly elastic collision. The second problem in my exam was the one asking about the velocity of a bullet found by basically it striking a wooden block that rises up by 12 millimeters. So in order to calculate for this problem, you're going to try and find the velocity that the mass of the bullet and block system has to be in order for it to rise the system by 12 millimeters. In order to do that, what you can do is use basically potential energy and kinetic energy formulas that I have here. I don't know if you guys can see that, but when you solve for this, you're going to initially put in that the mass of the bullet and the block times gravity times height of the bullet and block is 9.41505. So that's your potential energy. So if you know the potential energy of this system, the amount of energy it has at the top of its arc, then you know the amount of energy that it must have had in kinetic energy at the bottom of the arc. Kinetic energy's formula is pretty simple. It's 1/2 times the mass of the bullet and block times the velocity of that squared. So since we know that that has to equal to 9.41 or 0.941505, we can then solve for the velocity of the bullet and block system, which is going to be the velocity of both equal to the square root of 2 times 0.941505 divided by the mass of the bullet and block system. So if I'm trying to write this out, the first thing I'm going to do is I'm going to take the mass of both the bullet and the block times gravity, which is 9.8 meters a second squared, times the height that it's risen by, which is 12 millimeters. And we'll divide that by 1,000 to get to meters. So this gives us our potential energy. And that, when we calculate it out, gives us that value I was rambling on about earlier, which is the 0.941505, right? And since we know that that's the potential energy, then we know that potential energy is going to be equal to the kinetic energy at the bottom. And kinetic energy is equal to 1/2 mv squared. If we want to use this formula to find the velocity of both at the bottom, we can break it down into velocity is going to be equal to the square root of 2 times our potential energy divided by the mass. When we calculate that out, what we're going to get is a velocity for both of, you calculate that out real quick. I missed that beforehand. .941505 divided by the mass, which is 8.006. So in my case, the velocity for both the bullet and the block at the bottom that I calculated out was 0.4849, whatever the heck. There's more numbers to it. That's probably going to be close enough. So that means at the bottom of this arc, right here, when the bullet is embedded in the block and they're both moving now, it's going at 0.4849 meters a second. And that's exactly the amount of velocity required to get this block to arc up by 12 millimeters. And we know that because we calculated the potential energy in order to find out the kinetic energy at the bottom. Now you're asking, well, how do you go from there to the velocity of the bullet? Well, that's pretty simple. Mass times velocity equals to mass times velocity. So if we take the mass of both the bullet and the block and we multiply it by this velocity here, and then we know the mass of the bullet over here, we can calculate for the velocity of the bullet. So the velocity of the bullet has to be equal to the mass of both times the velocity of both divided by the mass of the bullet. When we calculate that out, the value that we're going to get is going to be 647.117 meters a second. I apologize for not writing out all the numbers and everything, but I figure if I'm giving you the formulas, you'll be able to plug your own stuff in. So I'm just going to give you the formulas and the results that I get when using them so you can cross-check with that. If you need to see what numbers I'm plugging in, hopefully you can see it on my laptop screen there. The third problem that I got. So this one is the one to deal with an ideal spring, a weight, and asking for the work that's done. So for this one, you need to know a certain formula. You need to calculate for the spring constant first and then plug that back into this formula to see how much work is done. The formula for work of a spring system is going to be 1/2 times K, which is your spring constant, this is something you'll need to know, times the displacement, so how far the spring is stretched or compressed, squared. So in this problem, you don't know the spring constant, but however, you do know the displacement and the amount of work done for that first displacement. So in my case, it was that the work done was 90 joules in order to displace it by 0.5 centimeters. Now, I can't use centimeters in this formula, so I'm going to divide it by 100 to get to meters. So that's my displacement. Square that. 1/2 times my K times that has to equal to the 90 joules. So if I want to solve for K itself, what is K going to be equal to? Well, in our case, K is going to be equal to 2 times the work, which is 90 joules, divided by the displacement squared, which in our case is 0.5 centimeters divided by 100 squared. When I plug that in, I'm going to get a really big number. Don't worry about that. It's normal. Your K value is probably going to be pretty big in most problems. In my case, it's 7.2 million. Now, if I plug this into this problem here, I can solve the amount of work done for any displacement. So what I'm going to do, work is equal to 1/2 times the 7.2 million, I'm just going to shorthand that, times the displacement squared. The displacement that it's asking me about for this problem is 0.6 centimeters, or 0.6 centimeters. So if I take that and divide it by 100 to get to meters, and I square that, the result for how much work I'm going to get is going to be equal to 129.6 joules. And that's how you solve for this problem. My next problem is asking about an external force applied to a box and the amount of work that is done by friction. For this one, I can't really explain how I got the formula, but the formula specifically for it is that the work done by friction is going to be equal to 1/2 times the mass times velocity final squared minus velocity initial squared minus the work done by the force applied. So when I plug in my values, I'm just going to put WF to represent work friction. I'm going to get 1/2 times the 20 kilogram mass times my velocity final is 8 meters a second minus 10 meters a second squared minus the work done by the force imparted. So for the work done by the force imparted, that is basically just going to be the amount of force that you're using, so 120 newtons, times cosine of 30, because that's the angle, times the distance that it's done across, which is 8 meters. When I solve for that and I plug that up into there, this whole formula is going to output one number. That's all I need, the work done by friction. And that value I'm going to get is negative 1,191.38 joules. And that's all there is to this problem. Basically, you just need to know this formula and work it out from there. So the next problem that I have is, how fast would a 70 kilogram person have to be running in order to have the same amount of kinetic energy that a 250 watt light bulb uses in 180 seconds? So this one is pretty simple. You need to find the energy that a light bulb uses in that given time. So energy, and that's equal to the wattage times the time. And then using that energy there, we need to figure out how fast a 70 kilogram person would have to be running to have that same amount of energy in kinetic energy. So first we'll solve for the energy. That's wattage times time. So in my case, it's 250 watts times 180 seconds. It's important to note that the time has to be in seconds. You can't plug in minutes. So if I tried to plug in 3 minutes here, I'd get an entirely wrong answer. Convert any time unit into seconds. So that gets us an energy of, where is it? Apologies about this. 45,000 joules. So now we know that the kinetic energy, we have to solve to get to that. And what is kinetic energy? Well, kinetic energy, as we've used before, is 1/2 mass times velocity squared. So we already know the mass, 70 kilograms. We want to find the velocity. And we know the kinetic energy has to be equal to that value. So if we use this formula here to figure out what velocity is, we're going to get that the velocity is equal to the square root of 2 times our kinetic energy, which is the 45,000 joules, divided by the mass, which is 70 kilograms. When we plug this in, the value that we're going to get is the velocity that this person would have to be running to get the same amount of energy as that is going to be 35.86 meters a second. And that's our answer. The next problem that I have. So this one is asking about the power required for an elevator to lift 60 or 50 people that are 90 kilograms each by 70 meters. So this one is fairly simple if you know the formulas. So first we need to know that power is just equal to work by time. Well, we already know the time. That's in 1 minute. We don't know, however, the work, but we can calculate for the work. So work is all just force times displacement. Well, what's the force? Well, the force is just going to be however much these people weigh times the gravity. So you have 50 people that each weigh 90 kilograms. We multiply that by 9.8 meters a second squared, and that gives us our force. We multiply that by our displacement, which is 70 meters, right? This is equal to the work. So when we calculate for that, our work that we calculate is going to be equal to 3,087,000. So that's our work. And also, actually, I apologize, I got this wrong. It's work divided by time. So when we plug this back into here, power is equal to work divided by time. We take our 3,087,000, we divide it by the time. Well, in 1 minute, how many seconds is there? 60. If we take this value, we divide it by time, we're going to get our actual value of our power being 51,450 watts. That's all you need to know for this problem. Next, number 7. So this one is saying during a collision with a wall, the velocity of a 0.8 kilogram ball changes from 25 meters a second towards the wall to 10 meters a second away from the wall. If the time the ball was in contact with the wall was 0.7 seconds, what's the magnitude of the average force? So, well, we want to find the average force. What is an average force going to be equal to? Well, do you remember F equals ma? So that means our average force is just going to be equal to our mass times our acceleration. You'll notice, however, there wasn't an acceleration given in the problem. We do, however, have a mass, and acceleration can be calculated with the values that were given there. Our acceleration is going to be equal to our delta v, and our delta v is basically just going to be the two values of velocity before and after it hits the wall. You can just add those up. So in my case, 25 meters a second plus 10 meters a second. And if we take that and we divide it by time, which in my case is 0.7 seconds, that'll get us our acceleration. In my case, the acceleration calculated, when I plug that back in up to here, multiplied by the mass, I'm going to get an average force of 40 newtons. And that's all there is to this problem. You basically need to know that F equals ma, and that works for average as well. And then in order to get the acceleration, it's going to be your delta v, so the difference in velocity before it hits the wall and after, divided by the time. And that's all there is to that problem. Okay, next, number 8. This is basically just a problem about kinetic energy and potential energy. So as we already know, in a problem like this, kinetic energy has to be equal to potential energy. And it's saying that there is a ball up here that weighs 0.4 kilograms hooked onto a string that is 35 centimeters long. Well, we know that the difference in height has to be 35 centimeters just because of how that works. So potential energy is equal to mass times gravity times height. Well, we know our mass is 0.4 kilograms. Gravity is 9.8 meters a second squared. And we know our height is 35 centimeters. Not 0.35. 35 centimeters divided by 100 to get to meters. So if we plug that in, our potential energy that we get is equal to 1.372 joules. Now we know that our kinetic energy has to equal this value. Kinetic energy is just 1/2 mv squared. However, we want to solve for velocity, not kinetic energy or anything. So we're going to turn this formula into 2 times kinetic energy divided by mass. So when we plug all our numbers in, we're going to get square root of 2 times 1.372 joules divided by the mass, which in our case is 0.4 kilograms. If we plug all of that in, our value that we're going to get is going to be 2.619 meters per second. And that's the velocity the ball has to have at the bottom here. The next problem, it's a bit funky. I would explain the formulas, but honestly, you don't need them. So this is saying that you have two masses. This is the dumbbell problem, by the way, right? And the rod is of negligible mass itself. So if we have two masses here, these are the only weights we need to take into account. Moment of inertia is basically how much momentum an object has when it's rotating. So the first thing is asking if you have an axis passing through the center of the rod here and perpendicular to it. So that means these objects here would be rotating about like this. The second case it gives me is where the axis is actually through one of the dumbbells itself. So that means I have a mass right here on top of the axis and one way far away from the axis. So in terms of moment of inertia, a weight that is further away from the axis is going to increase the moment of inertia a lot more than one that's close to the axis. So with this case, let's say our radius is just going to be a unit of 1. So this one, you have two masses that are both each a unit of 1 away from the axis. With this case, however, you have a distance of 2, you have one mass that is right on top of it, and one mass that is a unit of 2 away from the axis. When I move something away by a unit of 2, even if it's half the mass of both of these combined, it's going to have more of an effect on moment of inertia because distance from the axis affects moment of inertia more than the amount of mass. So in this case here has a higher MOI than that one. And that's all you need to know for this problem. The last problem that I'm going to be recording today is the two cars hitting each other. Now this problem, the correct answer on Pearson is wrong. I'm going to show you how to get the answer that I put in that I got correct afterwards. So for this problem, I'm going to draw a little diagram. You have one car traveling north at 25 meters a second. And this car weighs 800 kilograms. You also have another car that's traveling east at 33 meters a second. And this one weighs 1100 kilograms. Well, you might need to know, how are you going to figure out the final velocity? Well, I don't need to figure out the final velocity itself. I can figure out the velocity in each direction. So the formula that I'm going to use is mass times velocity is equal to mass times velocity. Well, how am I going to use that? Well, what if I plugged in the mass of just one car times the velocity of that car in only one direction? And then the mass of both cars, that would give me the velocity. So if I want to solve for the velocity in, let's say, the y direction, all that I need to do for that is I need to get my 800 kilogram car that's traveling by 25 meters a second. I take that and I divide it by the mass of both cars, which is 1900 kilograms. And that gets me a velocity in the y direction of 10.526 meters a second. I'm going to do the same thing for the x-axis. So my velocity in the x-axis, that's the car going this way. Well, the mass of that car is 1100 kilograms. The velocity of it is 33 meters a second. I divide that by the mass of both cars, which is 1900 kilograms. And that gets me a velocity in the x direction of 19.105 meters per second. Now, this is just velocities in each direction. I need to put them together. Well, that's pretty simple. Square root of velocity in y squared plus velocity in x squared. That gets me a final velocity of 21.813 meters a second. But this question also asked me for a direction. So if I graph these two velocities that I calculated, right? I have velocity in the x direction of 19.103 meters per second. And I have a velocity in the y direction of 10.526. And this question is asking me about the direction in terms of degrees east of north, which means my angle that I want to calculate for is this here. So in order to do that, I can use tangent. Tangent is equal to opposite over adjacent. This is a simple trig. If you don't know it, don't worry about it. Just know this. So in this case, I'm going to plug in the opposite. In that case, that's whatever value that is. So that's my 19.103. Divided by my adjacent, which is the 10.529. When I plug this in, the angle that I'm going to get is going to be 61.147 degrees east of north. And that's all I need for this problem. And I think that's actually about all that I'm going to be doing for today. So, yeah. If you guys have any questions, feel free to put them in the comments, tag me and group me, whatever. I'll probably try and respond pretty quickly, but there you go.